Welcome everyone to the 2020 World Meteorological Organization HIWeather Workshop webinar series. Today we'll be seeing the second of 5 seminars, this one on understanding, monitoring, and estimating weather-related risk and impact. My name's Brian Mills. I'm a social scientist with Environment and Climate Change Canada and based at the University of Waterloo. And again, I'd like to welcome you to today's talk. As I said, it's one of a series. Some of you may have joined us last week for a seminar regarding communication about high impact weather on the 26th of October. That recording will soon be available. And looking ahead, we see seminars scheduled for evaluation, hazard forecasting, and weather processes later in the year. So please continue to join us, share your thoughts, and we'll get going. So today's agenda, again, the title, Understanding, Monitoring, Estimating Weather-Related Risk and Impact. Never ask a researcher to develop a pithy title. I wasn't happy with impact-based forecasting. Your host today, in addition to myself, I'm joined by Martin Wegman from WMO. He's been an essential linchpin in both technically and content-wise aiding us. He's resolved a number of issues for us neophytes dealing with Microsoft Teams live event. Today's lineup is listed there, so I'm going to give an overview talk for a few minutes, get a little bit of my own research in there, and that will be followed by really the core of the session, talks by Isabel Ruin, Sarah Harrison, James Daniel, and Jeffrey Lazo. That will round out the discussion. 15 minutes talks plus 5 minutes Q&A, time permitting, after each presenter. You can ask your questions if you join the chat function. You'll see a chat box on the right side of your screen line up, and you can ask your questions there. What I'd ask you to do while I'm presenting the first talk is to maybe just chime in with your name and your organization or your general interest in this topic or high weather generally. And that will kind of give you a feel for how it works. And then as we're going through the presentations, we encourage you to write down any questions you have as you think of them. And that will give us a head start. There's a little bit of a time lag between when you write something and when we see it. And Martin and I will be monitoring that and raising a few of the questions after each presentation, and then at a general discussion session at the end, time permitting. Okay. So let's get started. So the context for the impacts, vulnerability, and risk task team of the HIWeather project and the HIWeather project. So it's nested within this UN agency called the World Meteorological Organization. It's been reorganized recently into a Services Commission, Infrastructure Commission, Research Board, regional associations, etc. on the schematic there. This project is nested inside the Research Board and the World Weather Research Program, which I hope you can see on your screen. This program is really responsible for advancing, promoting research activities on weather, its prediction, and its impact on society. It's composed of working groups, regional activities, joint activities, and most pertinent to our discussion today, core projects. That includes the Polar Prediction Project and Seasonal Prediction Project that some of you may be involved with or are interested in. The difference with HIWeather is that we tend to have a dominant role of social and interdisciplinary science in this research project. So the HIWeather really is aiming to deliver a blueprint for the warning system of the future by focusing on critical aspects of the end-to-end warning chain from observation to forecast to response. It has a limited set of hazards, although they're fairly broad. 5 of them are listed here. And we're really dealing with phenomena that have a life cycle and predictability of from minutes to 2 weeks. Governance in the project, there's an advisory board and international coordinating office based in Beijing, China. The co-leads who have been instrumental in getting us to where we are, Brian Golding and David Johnston, and of course the task teams, which are really the structure we're using to present the webinars. Communication, evaluation, multi-scale forecasting, predictability and processes, and today's focus, impacts, vulnerability, and risk. We have a number of members that are active. 2 of these folks in the list there, Urbano and Danielle, have just joined us, so we're just getting the feet wet. All of these people have a lot of experience either as practitioners or as developing their own research programs in this area of research. They're often bridgers, so they combine aspects of physical and social or interdisciplinary science, and that's kind of the ingredient. If you're one of these people out there, please feel free to email me if you want to join us, if you like what you're hearing and feel like you can make a contribution. And it's all voluntary, but I think behind in the background, you'll see that it's really a network type activity where the actual benefit is in establishing a broader network and taking advantage of what we know all around the world. Kind of like the Eagles lyric, you can check out anytime you want, but you can never really get away. We have members emeritus, including Jeff Lazo, who's here with us today to present. So you never really leave us, you just go gray for a while. Okay. What's kind of like the main conceptual framework in the task team? Well, the conceptualization of risk, we follow the standard kind of approach that risk is an expectation of impact or outcome, which in itself is a function of the likelihood of a particular hazard event or events or attributes of those events, and the consequences, which gets us into more of the exposure and vulnerability side, the social side of the equation. Now, as many of you already know quite well, that national weather services have been really moving from just focusing on that hazard event thresholds of X millimeters of rainfall or wind speed to understanding or try to communicate how that might affect people. So going from hazard forecasting and warning to risk or impact-based forecasting warning. And WMO has been quite supportive of this in their services side of the house. They put together a better practices document that's currently being updated, and we have exchanges with that side as well. But our focus is on research. Another heuristic or a conceptual tool we use to kind of understand this is an impact-based forecast is kind of like an intervention. We're trying to influence behavior practices. And this is a way to conceive that from the left to the right, we can see that there's our weather or water or climate related risks. We have a kind of a service production function that's a mixture of different components within National Weather Services, for example. This gets mixed with private sector and other agency information. And ultimately, we're trying to produce something that influences user decisions and actions, and more importantly, to the idea of impact at the end of the pipe. What are the outcomes of those processes? You can see the home publication there for this. It's really the intellectual property, I think, of Jeff Lazo. I thank him for that. What is an outcome? Well, at a very micro level, and something that I'm really interested in, we can think of motor vehicle collisions. And I know the person in this collision had permission to use his footage. But as you can see, even at a micro level, we see that there are different categories of impact. Injuries, damage to vehicles in this case, or road infrastructure, light poles, critical service interruption, whether it's, not so much in this case at a micro level, but transportation for sure. That intersection was blocked off, no doubt, for hours. Dislocation, not too much, a little social disruption, economic effects at the household or individual level, sure. And opportunity costs of response or intervention. It costs money to have insurance or to have particular safety features in your vehicle that help keep you safe. So these are just the overview of the types. What we're really interested, though, is what difference does weather make to the incidence of things like that occur on a very micro scale but can be rolled up. And some work we did on motor vehicle collisions in winter storms is presented here. I'm going to show you basically what is one winter weather event, a lake effect snow event in southern Ontario. The area outlined in red is the case study area, a large regional municipality of about 600,000 people west of Toronto, Ontario, Canada, and the Great Lakes, Lake Huron there you can see in the upper part of the screen. What this is just an overlay of basically collision counts that occurred during this event over a number of hours. So hourly sums of collisions, half-hourly radar imagery, so you'll see it move 2 images per hour, and then some surface data, surface variable from the local airport, temperature in red, dew point in green, wind speed in kilometers per hour on the barbs, and visibility in blue. So you can see as the event proceeds, the total length of the bar basically tells you how many collisions were occurring at that event. We then want to know what the excess is. So we use a technique called matched pair analysis and go back 1 week, so same exposure generally in time and date, and track the number of collisions that would have occurred anyway, perhaps, and that's indicated in red, that proportion. And what you get at the end of the day is a crude risk ratio. Okay, the publication there, where the data is discussed, is presented at the bottom. This is just more of an indication. When you roll all that up over hundreds of events, many years, you can develop a statistical analysis of relative risk. In this case, the dots represent mean estimates of relative risk of injury collisions, so more important than just general collisions. And we see at 1.66, that means, or the confidence intervals are presented there too, that between 47 and 88% more collisions tend to occur when we have winter weather events as defined in the study, and the comparable figures are on the right at the top of the graph for non-injury collisions. The most important thing to note, or important things, is that this is really variable. It varies by the size of the event, the nature of the precipitation in the event, the duration, etc. And it also importantly can be associated with when we have winter weather warnings in effect, snowfall warnings, winter storm warnings in the case of the Meteorological Service of Canada. We find that 75% of these impactful events don't go warned. And that's not surprising because we know intuitively that a little bit of snow goes a long way in this particular risk. Okay, the important thing to think of is how can we start taking knowledge from studies like that, which tend to be very small focused, and bring them into our thinking on how we present impact-based warnings. And here's a few examples at a generic level of how some countries, from the left to the right, South Africa, the Met Office in the UK, and a particular test product from the National Weather Service in the States, are presenting or trying to incorporate an understanding of categorical impact or risk. The one on the bottom is from Ontario region of the Meteorological Service of Canada, Environment and Climate Change Canada. So really the task is to figure out the primary questions here. How do we take advantage of that knowledge and look at these services that are out there or being contemplated, and look at how the extent, type, and quality of impact, vulnerability, and risk knowledge is used to design, operate, evaluate, improve impact-based forecast and warning services. And then to what extent do these services, the advantage of this WMO international program is that we can share across jurisdictions, cultures, social, and hazard contexts. Well, how transferable are they? What lessons can be learned or shared? The second part of this, and one that I've found a number of agencies are dealing with or grappling with at the moment, as well as some of us on the research side, are trying to understand how effective impact-based forecast and warning services are relative to traditional meteorological warnings and forecasts, or mixes of them. So the content mixed with, as in the communication webinar the previous week, how you present that information. And then to what extent can these types of new services address knowledge, action, or belief, intention, behavior gaps? So why, when we say something that we're going to do, we don't actually do it? And that brings both of these questions cut across all of the task teams in the HIWeather project. They're particularly pertinent when we're talking about impact-based or risk-based forecast and warning systems. So that's really infusing the raison d'etre for our research. And it's still moving slowly. It's a tough task, but some of the activities are listed here. The big one is a review and critical assessment of weather-related knowledge, impact, vulnerability, and risk knowledge, modeling and relatable evidence to support impact-based services developed by national services, but relevant for others. And this includes trying to bring in scans of public-facing services that are out there, a working inventory, and trying to make sense of the quality of knowledge that's in place now, the process that we use to build these things, and then how can they be improved as new knowledge becomes available about impacts, vulnerability, and risk related to weather. Okay. Another activity is just general support for the 3 cross-cutting HIWeather activities. That includes citizen science, the value chain approaches to evaluate the end-to-end warning chain, and a large publication, a book towards the perfect warning. And also related efforts in WMO in different parts, so like the update to the multi-hazard impact-based forecasting and warning service guidelines that we mentioned, also regional training workshops. So those 3 items there, those 3 cross-cutting activities are the focus of the workshop in December. And all of these seminars kind of build towards that. We encourage you to submit abstracts if you haven't already towards the workshop, and hopefully we can fit everyone in to present. Other items is just continuing to expand. If you looked at the list of members, we need to kind of develop a little better representation internationally. And finally, I think there's a room to really build on that second question that cuts across all of the task teams in the HIWeather project. And that's really looking at trying to develop a methodological toolkit to design and assess the efficacy of impact-based forecast and warning services, but really any change or intervention that national services infuse into their systems. How can we best track, monitor, and evaluate that to hopefully make at the end of the day, assess what benefit we've developed and what changes could be made to make it even better. Okay, so I'm going to end there. Our next person, I'll take a question or 2, I guess, and if there are any, I'm just going to get out of here, I think. Okay. I'll give a minute or 2 for people if they have any key questions. I know I went pretty quickly there. Catch a drink. Our the deathly science is troubling. Can anyone give me an indication by typing a message that they're here? Martin, are you still there? Okay, good. It is unusual. Okay, there we go. Okay, I don't see any questions, so let's move on. I'll stop sharing my screen, and we're going to turn to the next presenter, Isabel Ruin. And she's going to talk to us about integrating dynamic human exposure and vulnerability in flood impact-based forecasts.
Do you see my screen? Full screen, hopefully. Do you see the full screen?
I do. I think it's good.
Okay, perfect. Thank you very much, Brian. I'm Isabelle Ruin, and I'm going to present the work that I've been doing with Galatea 30. So we are from France, and the CNRS and the Institute of Geoscience of the Environment. I'm a social geographer, and I've been studying mostly vulnerability to flash floods, and from basically observation of especially behaviors during crisis toward modeling those behaviors and integrating them to kind of impact-based forecasts. So that's what I'm going to talk about today, and we're giving you some examples from 3 projects related to that. So here, next slide. So basically, what do we want to do with impact-based forecasting? Basically, it's related to the understanding of the social and behavioral driver of impact variability. So basically, to forecast those variability related to different parameters that could be either from the hazard side or from the social vulnerability side. And the objective of this impact-based forecasting is to limit direct and also indirect impacts of the threatening events, and basically to help decision makers to make sense of the situation, the detection of the situation toward the crisis, and to basically adopt appropriate and timely actions. So on this slide, you can see that there's, of course, several components to take into account to be able to do impact-based forecasting. And of course, one is the weather hazards, and it's not what I'm going to talk most about, but mostly I'm going to concentrate on how to integrate social and physical vulnerability into those forecasts. So social and physical vulnerability are related to 3 main components. One is exposure, and exposure is basically the spatial and temporal conjunction of the hazard and the elements that are at stake. As you can see here, it's basically all the elements that you can see in the blue bubbles in the middle. The sensitivity would be related to the degree to which humans, environment, and social ecological systems may be affected by specific hazards. So, of course, if you have a basement floor, a floor base at the basement, apartment at the basement, and if it gets flooded, there's the big chance that you would be affected. But if you have 2-story houses, then you can go upstairs and you still affect, but it could be less, let's say, dramatic. So that's an example. But the second thing, third component is the coping capacity, and it's really related to how the system or elements of the system can adapt and accommodate to basically avoid adverse effects. So it's related to how people can behave to avoid the effects, but not only people, but also the organizations of the society, like warnings and things like that would be under this category somehow. So just to show you that basically, if I go back, sorry, to this previous slide, I mean, this slide looks like a little bit of static things, but actually what's the problem is that everything moves in space and time. I mean, the hazard would be evolving and increasing or decreasing of the flood, and at the same time, the society is also related, is also driven by rhythm, like social rhythms. So you're not all the time in your schools or in your home, you move, and some elements are more important during some times of the day, while other would be more important during the night. So this is very much to take into account. And as you can see in this second slide, if we looked at, when we look at flood fatalities in U.S., so in like 15, more than 15 years of data sets, and we looked at more than 1,000 fatalities for about 700 events. And you can see that depending on the circumstances of the fatalities, there is a very different temporal patterns of the fatalities or the accidents that conduct to fatalities. And we can see here there's 6 different circumstances. The first one, which drives the most of the fatalities, are nature related. And the second one would be the campground and recreation outside, like close to stream or in the open air. You have also a permanent building, a mobile home, and other things. And as you can see here, and the colors relate to the number of victims, red is a higher number. You can see that in some circumstances, some circumstances are completely different, show completely different patterns than others. If you look at the vehicle related, of course, you would see that the timing is more related to the timing of the going to work or coming back from work, and also the evening life related to activity like shopping or outside social things. If you look at campsite and things like that, it would be more related to activities that you might have either during the night because you're sleeping in a tent and you're not protected at all, or during the day where you're doing activities like in canyons or things like that. For the outside, finally, most of the fatalities happen during daylight hours, when people are doing errands and leisurely activities in the outside. Permanent buildings are more related to the evening when actually there's a rise of the water, and when people start to get a bit worried during darker conditions. So basically, you can see that there's very different patterns depending on the situation. So those situations and the activity of people are very much to take into account if you want to predict somehow your impacts on people. For instance, one way of predicting is also to look at what is the routine, the usual activity-based travel patterns. And these types of data can be extracted from census data. And as you can see here, it's a representation of the different types of or proportion of people doing different types of activity during different hours of the day. And you can see, of course, that a lot of these activities are also related to travel patterns, routine travel patterns that figure here in a pink, red pink. And of course, if you don't take that into account and these 2 bumps here, then you don't really, you can't really draw a picture of where people are and what they are doing and how they can be affected in those different circumstances. So it is important to take that into account. So from these first observations and from data and things like that, we also, and of course from theories, many people have social scientists have worked on this domain, and what we propose here is a theoretical scheme to show how to integrate somehow those different aspects of exposure, sensitivity, and coping capacity, and looking at both fast evolving processes and slow evolving processes, and how those would make would trigger different types of impacts, either high or low impacts. So related to that, of course, you have some risk governance parameters, land use, which are more static. Also individual status, which would be related to their physical conditions, social capital, socioeconomic dependencies, but also more cognitive aspects that would be related to risk perception or cognitive mapping and related to coping capacity. All these, of course, is kind of longer term kind of processes, but you can look also at shorter term processes related to how people, based on these background, let's say, would have different perception of the situation and how they consider the crisis circumstances and how they can react or cope with those specific circumstances based on the coupled place activity where they are at and what they are doing at that time. All these will condition how they make sense of the situation and how they decide what to do in that case. So based on this scheme, we basically propose a different modeling approach, and I will now detail two of them, basically coming from different projects. One is related to a project that we had with the National Severe Storm Laboratory in U.S., and which concerned actually the old U.S. to do some human impact forecasting for flash floods at the resolution of the census tract. And the other is related to a French project called MobiClimax, and which is related to the mobility modeling, the mob risk dynamic model. And the resolution is much higher, kilometer, but it concerns a smaller part of the smaller geographical extent, for instance. So I'll go to the first model, and of course for this model, I mean, it's the statistical model, and we started from learning from fatality data, which are very important data sets that comes from the NCDC storm database. And based on those data, basically looking at what was the characteristics of the people who died from flooding in the past 20 or so years, we looked at those differences in terms of gender and also ages related to those different circumstances that I talked about earlier. As you can see, of course, the most dangerous circumstances is related to vehicle related, then followed by outside close to stream circumstances, and then a campground or recreational area, and then permanent building and mobile home. As you can see, those circumstances are somehow different if you look at the number of flash flood by fatal events, as the campground circumstances would make more people would die more a bigger number for each event. Anyway, what we figured out from that is that, of course, these different circumstances are also linked with different socio-demographic characteristics of the people. For instance, vehicle-related would be more middle-aged people, as well as campground and recreation area. Outside is more related to younger people, and elderly are for permanent building, and the middle age is more related to mobile home. There's also a big difference in between the genders for the faster reactions of the catchment, so more flash flooding situation for vehicle-related outside and campground. It's more related to male. I mean, male are more often in trouble than women. And the other circumstances are more related to elderly and middle age, and somehow it's more mixed between male and women. How did we do from there? Basically, we and Galatia did this work, Galatia 30. She basically built a big database with all the entry of the different events. And she built another database related, which would be adding different proxy variable that represent the different vulnerability and exposure factors. Based on that, machine learning modeling was used to classify the accident that gave fatalities and the one that gave no fatalities, and to basically figure out which were the important drivers of these differentiation between the two. Based on that, she was able to build this model, and this model was done for the whole U.S. and at the scale of the county. And as you can see here, for the state of Texas on the case study, Texas and Oklahoma, we also compare the results of these probability of human risk related to vehicle accidents to the red points, to the observation related to fatalities and also social media. And as we can see, it works. It's of course not perfect, but it works quite well, and it's a very encouraging result to go this direction with random forest modeling. As we have seen from this modeling, the unit stream flow and precipitation duration, and also the number of commuters arriving by vehicle in the workplace were very dominant factors triggering the result. Now I would like to go to another example, the one in France, for the mob risk, which took a different way of modeling because we didn't have access to that very detailed impact data. So we had to figure out another way to do it, which is called the discrete event simulator, which is quite close to something that is called agent-based modeling. And to do that, we of course have a database, and this simulator helps to put together the dynamic of the environment from modeling of the hazard, the dynamic of the individual and their mobility, and coping behaviors. So we have several models that put together all this in action to see interactions between those and the result in terms of probability of accidents. Of course, you need to define a space-time window and to run the model for a specific event. So we did for past event to start with. So basically, it uses data about road submersion and the probability of road submersion of this road from hazard modeling, and also a road user exposure, which use activity-based mobility model and decision-making models that I will show you soon. So the first is an activity-based approach, which is the mobility is a result of the need to conduct activity, which are distributed in space and time, and all this can be done from census data that propose a daily schedule that you can attribute to people based on their socioeconomic characteristics. Then you can locate this activity in space related to also census data. So you know where residential places are or where working places are, and all the road networks. And then you have to look for, of course, how people choose their route, and we use the shorter path algorithm here. Then we use another model called, it's a Bayesian model to take into account copying behavior. And the idea with that is to basically look at how people would behave based on different observable variables like environmental sign, trip purposes, as we consider that the flexibility of trips are very depending on the type of the mobility, the purpose of your trips. And all these would come to an evaluation of danger and an evaluation of the trip flexibility that will influence the decisions to adapt or not your trip and to cancel your trip, to go back home, to replanify or your activities. And this is all ways to also test hypotheses of what would it change, for instance, if you would give another type of alarm you change the lead time, or you change different the timing of the event. It would be like, instead of being in the night, it would be in the day or things like that. So you can all play with that. The result is also something that we can look at in terms of the differences of exposure of the people, which is the point line, and the black line, which are the people that are potentially in danger. By crossing this, basically the probability of flooding of the roads where people go. So basically, you look at the itinerary of people, daily itinerary based on their mobility, daily mobility, and how these daily mobilities and itinerary are basically impacted by the current flooding. And then you add this component of decision making when they are in front of flooding, or where they start a new activity. And all these give you some kind of quantitative evaluation of the number of people that would be in danger in such circumstances. Now I would like to end this presentation with a new technique of modeling that we now currently develop. It's related to agent-based modeling, and this time it's even more small scale, as it really target the decision of agents, and how agents, which are the people in crisis, and how those different decisions may, so how agents between each other would interact and would come up with a potentially collective decision or emergent situation, but also how agents would interact with the evolving environment. So this is an idea of how we can put all the observation of behaviors and understanding that we had so far, based on very different types of studies, empirical and theoretical knowledge that we gained from past experience, to basically model and code all these different behaviors into agent-based modeling, where you can also couple the dynamic of the environment, the warning, the evacuation, some alerts and things like that, to see how all this would interact to come up with different types of impacts. So that was very fast, I'm sorry. I'm going to go to conclusion now, and hopefully if you have any questions. So for all these kind of modelings, which include vulnerability, exposure, and of course, which also integrate hazard modelings, models anyway needs to be adapted to the users. So what type of impact do you want to model? And you really need to have the user on board since the beginning of your development. And it is also very good to have a user group that you can interact with. It's also very important to learn about critical weather patterns, thresholds from those who are impacted. So looking at using different types of data collection, either it could be interviews to have very rich information, or more like questionnaire survey, using high resolution things, and also, if possible, having a view of all this on the longer time period. Also, the last point is that modeling, even in social science, needs observation and data for calibration, validation. So we really need to merge traditional social science methods with new participatory methods like social media, crowdsourced data sets, fierce games. All these would be very interesting tools, even though for now, I mean, the methodology to use them in a robust way is still under progress. So hopefully, I hope this was not too fast, and I would like to take a question if you have any. Thank you very much.
Thanks, Isabel. That was really great. A lot of content in a short period of time.
Too much.
Thanks so much. No, it's fine. I think you've got a couple of really good questions. I'm going to try and tie the two together because we're just, we're running. This is an experiment in MS Teams as we go through this. So from René Sieber and Armel Castellan, two questions about how basically how we transfer this type of approach or knowledge One from Renee Moore, is it really transferable to other places, and what would be needed done to make it transferable? And the second one is more related to how you can use this in an operational forecasting or warning center context. So how do you successfully bring this into an operational environment and have the desk forecaster, I guess, change their approach in real time or near real time to take advantage of this, input of information?
Yeah. Okay, so for the first, the transferability, this is very much related to the data set you have, and yeah, also the objective. I mean, the scale at which you want to work. If it's for the whole country, as the example of US that I showed, or if it's more localized, this is completely different. For instance, we couldn't use the same approach that we used for US in France because we didn't have any access to precise impact data. So it is very much related to these data sets. So this is the first thing to look at, is what data are available, can you learn from them? And if not, then you would need to go more on to more let's say scenario-based type of modeling, where you kind of put together the knowledge you gain from theoretical research, empirical research so far, but with not real data beyond that. So so this is how you would choose between the two. And then if I go to the second question, of course, also related to that, definitely the agent-based modeling or the discrete event simulator that I showed are quite difficult to integrate in an impact forecasting chain, because it takes some time to run this modeling. So, and not, it can't really be done in real time for now, because it's too much, it's too difficult, and the numerical prediction needs to do that quite fast. So nevertheless, those models that could be run in preparation, in before crisis or between crises, somehow to learn how to derive synthetic indicators from what you learn from those models. You could derive synthetic indicators from data sets that are existing. And then from there, you can use those synthetic indicators much more easily, I think, in the real-time forecasting process, I think.
Okay, thanks, Isabel. I think that's all the time we have for questions right now. I notice Marianne and perhaps others have listed questions. Keep the questions coming as you go through. We'll return to some at the end, and we'll also try and provide the questions to the researchers who are presenting as well, and they can develop more responses to specific inquiries later on, or follow up yourself later. So thanks again, Isabel, for a great talk and for the questions.
Thank you.
Sarah, you're next. I think everyone can see the agenda, hopefully, on the screen. I'm going to give up the screen again, and Sarah's going to be talking to us about developing an integrated impact, vulnerability, and exposure knowledge base for New Zealand.
Thanks, Brian. Okay. Hi, everyone. I'm Sarah Harrison, a PhD student at the Joint Centre for Disaster Research based in Massey University in Wellington, New Zealand. It's almost 4 a.m. here, so please bear with me if I'm a little bit slow in gathering my thoughts. So as Brian said, I'm going to walk you through some of my PhD research, which is broadly on developing an integrated impact, vulnerability, and exposure knowledge base for New Zealand. Brian, you said that you can actually come up with catchy titles, but you came up with this title, which I really loved, so I kept it. So I'm not going to spend too much time describing what impact-based forecasts and warnings are, because I think Brian and Isabel gave a pretty good background of it. But just to give you an example, this is from the WMO guidelines of an example of an impact warning. So extensive traffic delays in Kensington may occur due to the risk of large trees downing power lines and blocking roads as a result of severe thunderstorms. So there's a lot to unpack in this example. It gives some pretty specific location information and specific impact information. So in Kensington, it may occur, risk of large trees downing power lines, and then that's the result of this hazard, which is severe thunderstorms. Here's an example of an impact forecast or impact-based forecast from Ontario, which is where I'm from. I'm from Barrie, Ontario, originally in Canada. So this is from actually winter last year, almost a year ago, of snow day bus cancellation outlook. So this is produced by Instant Weather, which is an unofficial weather forecasting organization. But I really like this map because it really shows you what they calculated the chances of bus cancellations were as a result of an ice or a snowstorm. And this helped parents prepare if they needed to take time off work the next day because their kids couldn't go to school, or they needed to plan other ways to get their kids to school or to get childcare. So that's kind of a real life example. But what I've found in the literature and from talking to meteorologists and also civil defense practitioners is that there's a lot of data that's needed to support impact-based forecasts and warnings. First, we need the hazard data. Then we need exposure and vulnerability data, which Isabel described really, really well, and impact data. And a lot of the challenges are how to get all of this data, where to find it, and how to bring it all together to support a warning system. Basically how to operationalize it. So I'm trying to tackle this really big question and this really big challenge. So first, I identified in the literature like there's actually a lot of groups, people, organizations that hold this data. So we have insurance companies that might have impact data. We have governments that might have exposure or vulnerability data in the form of census. We have the public who also share and have impact data that they might post online on social media. We also have the media. And so there's, a whole bunch of sources. So how can we access it? Can we access it? Is it possible? And how can we use it? Is it usable? So my questions for my PhD research are, how is impact, exposure, and vulnerability data currently collected, stored, and shared in New Zealand? And how can this impact data support an impact-based forecasting and warning system for New Zealand? I'm taking a grounded theory methodology approach. I'm not going to go into it in too much depth, but it's basically an inductive methodology that's used in social science research typically to develop ideas and theories from observations and interviews. And so I've been interviewing officials from meteorological services, both within New Zealand and outside of New Zealand, as well as civil defense and emergency management officials from within New Zealand. And I've had about 27 interviews so far, and I'm in the process of running workshops to go in more depth with civil defense groups in New Zealand. So I've run one so far, I have another one planned in a couple weeks. So who are the people that I'm specifically talking to? I group them into 3 groups. I'm looking at people who look at data standards, custodianship, and maintenance, and then I'm looking at the data collectors, creators, and sharers, and I'm looking at the users. And there's actually a lot of overlap between these groups. So I'm not going to break it down here because of time, but some examples of the users would be risk modelers, but they could also be data collectors because they might go out and conduct post-event damage surveys that would be used for their risk modeling. So they would be also creators and collectors. And then the sharers could be Land Information New Zealand, which is also a custodianship role that they, produce geospatial information and then share it with other organizations or share it on their open data portal. But they're custodians of that data as well. So there's a lot of overlap, which kind of made my job easy. 3 birds with 1 stone. So I'm going to just walk you through some preliminary results that I have from one of my first round of interviews. And in this first round of interviews, I specifically focused on impact data and sources of that and how it can be used for impact-based forecasts and warnings. So first I asked, what were the data needs and the challenges with getting that data? So first of all, agencies really need to be able to trust the data. So, you know, the role of meteorological services in issuing warnings is to, you know, protect people and property. So they need to be perceived as trustworthy to stakeholders and the public. And so they need to be able to trust the data that they use to inform their decisions and their warning messages. This could be a problem for data sources like social media and crowdsourcing. It's not perceived as very trustworthy, so there's a lot of hesitation for them to turn to those data sources for impact information. Then we also need the systematic and standardized collection of the data. So many countries, including New Zealand, actually lack standardized and systematic collection of severe weather impact information. It's done by different groups at different levels. It's not very centralized, and they do it in their own way. There's not a lot of interoperability there, and it's hard to use them for any other purpose than what the data set was designed for. But if we can get systematic and standardized data collection happening, this could support evidence-based planning and decision-making and model comparison. And we need partnerships, data sharing and integration. So when I was talking to my participants, I found that many sources of impact data actually exist in many formats, as I said. And so we need these formal and informal partnerships, which may already exist, we just don't know about it, to share required information between agencies. And an example of kind of an informal partnership would be a telephone call from a hydrologist and a meteorologist from the New Zealand Met Service for them to say, heads up, this is what we're looking at. What do you think? Should we issue a warning, et cetera, et cetera? And they have these kinds of informal conversations, but they're really effective at sharing knowledge and information. But it is difficult, like I said, to integrate all these various formats of data in any meaningful way. And so I think that's a challenge that's beyond my PhD, but I'm trying to at least identify it and bring the attention to it. And then finally, data custodianship and cost. There's a big question mark of whose responsibility is it to collect and store all of this data, and how much is it going to cost, and how much money is actually available, how much funding is available. It's not in some agencies' remits to actually collect this data and take care of it. So for example, the Met Service in New Zealand, it's not in their remit to collect impact data. So whose job is it really? And again, that's a big question. That's more political beyond my PhD, but it's a fascinating question nonetheless. So some examples of existing and potential data sources that I identified from my interviews, specifically with regards to impact data. I found that there's kind of two groups of the data. There's official impact data and there's unofficial impact data. So crowdsourcing and citizen science and social media fall more under the unofficial impact data, and some agencies use it as monitoring the situation, verifying their warnings, sort of ad hoc on the fly. Some organizations actually specifically collect it and put it into their database. For example, in Europe, we have the European Weather Observer in Austria, MPing in the U.S.A, and WeatherX in Australia. And they take those crowdsourced reports and verify and put it in their database for further analysis. And then we also have two sort of timescales. We have real-time or near real-time and post-event impact data. So the crowdsourcing and the citizen science and the social media, the real value in that data is its real-time or near real-time aspect of it. But again, like I said, the trustworthiness is, well, the perceived trustworthiness of it isn't so high. And then for post-event impact data, this is, the higher quality, more trusted data. So this includes impact assessments, media reports, and call center data, and then, existing event databases, some of which Isabel tapped into. And then we also have tacit knowledge and experience, like I said, hydrologists and meteorologists kind of calling each other up and saying, we've seen this happen before, so we should prepare, etc. So overall, for data uses, so far I've identified two, but I'm sure there's many more. Uses of this data for impact-based forecast and warning specifically. So first of all, it's very useful for verification and validation of the warning or the model. So it can verify what happened on the ground using real impact information. And it can help meteorologists determine if they're under warning or over warning and strive for the right buoyancy of the warnings, as one of my participants said. And like I said, the real-time data is highly valuable for verifying and updating warnings on the fly. The other use is for actually defining thresholds for the warnings. So a lot of warnings traditionally are, the thresholds are based on the physical characteristics of the hazard. If we want to go to true impact warnings, we need to rethink and potentially redefine the thresholds so that they're more impact-based. So historical data could be used to prevent history from repeating itself, as another participant said, by allowing officials to identify trigger points, aka thresholds based on past events. So key findings are basically what I just said, but what I would like to highlight is that the limitations of this preliminary results is that I haven't covered vulnerability and exposure data, and those, like Isabel said, are really important considerations into impact-based forecasts and warnings. So that's the next steps of my PhD research. And so far I have, this is my conceptual knowledge base. I figured I should include it because that's what the title is. So it's this big framework of, first of all, on the left side is the data sources that I've identified, and I do have vulnerability and exposure data sources in there now, as well as hazard data sources. And then going into kind of what I've determined is the system box, but I'm probably going to rename that, and just basically how this data is all kind of funneled into either risk modeling or impact-oriented discussions, which are those more informal conversations, to then either define warning thresholds on the fly or define warning thresholds in advance, to then go in towards the decision-making for issuing an impact-based forecast or warning. So this is very much in development, and it will obviously change as I continue towards finishing my PhD. But the overall implications of my research is I have two sort of hopefully uses for my PhD. One is towards developing a national loss database for New Zealand, which is a priority under the Sunday framework, as well as furthering the efforts toward people-centered early warning systems, which I think impact-based warnings really fall under that. And then again, towards implementing impact-based forecasts and warnings in New Zealand. And thank you for this opportunity.
Thanks a lot, Sarah. That was very informative. A lot of work to build this, and a lot more ahead of you, it seems, still, but that's the nature of the beast. That's great. So you had a couple of comments or questions, and one's not directly related. Well, maybe it was related primarily to, I think, one of the graphics you showed about that private sector display of school bus closures or cancellations. And maybe it ties into the database in the sense of we don't always have to, I guess, build a giant database or have a plug and play type of impact model into that attaches to the numerical weather prediction that then gets vetted by the forecaster and put out into a warning process. In some cases, a good partnership with a group that's sensitive or vulnerable can bypass some of that, or maybe should be a lesson that we can bring into a database format as a lesson learned or an experience that we can all share. So Steve Goodman suggested that, or commented that in the States, in Huntsville, Alabama, the National Weather Service is really closely linked to schools, and that when there's a forecast for early rush hour precipitation, that the schools proactively announce through different channels of media that schools will start 2 hours later. So they kind of reduce exposure over that early period. It seems to work, and it's kind of a success story, it seems. I'm wondering, how do we incorporate that kind of information into a shareable database, whether it's in a specific country or overall? Any comments?
Yeah, that's a really good point. That's really good to know. I think really more at the local level or the county level. In New Zealand, we're going to go with the local level because we're so much smaller. But I think these relationships have really been developed between like civil defense and emergency management agencies and these interest groups or stakeholders like schools, hospitals, etc. And so I also heard of, for example, the hospitals here can have been in touch with the Met Service to say we actually have an increase in asthma cases for thunderstorms, so we need to think about this. So I'm still working on like how to capture that in a database. It might just be a matter of just identifying these partnerships and saying they're here, and if we want this kind of information, this is who we can go to. And it's more in real time ad hoc. But yeah, it's a really good point.
It's great. Thanks for that question. Yeah. So one final question. James asked one, but he'll be presenting next, so we can build it into his talk. It's more of a comment. I think he'll be talking about it. So as a Grandstrom, and I apologize if I'm mispronouncing names, I do like to say the names if I can, asks about, are there any issues regarding information security when you're collecting this data on vulnerability? So you can imagine there's an ethical aspect of this and all this work. Wonder if you could comment on that briefly.
Yeah, absolutely. So what I didn't highlight in my big framework picture was a box that was kind of on this issue of what are the barriers to getting this information and using it. One of them is definitely privacy, security, and ethical issues of getting the data. So if we're going to use this data, we have to make sure that the right measures are in place to protect it, to remove personal identifiable information from it. And there are some agencies, at least in New Zealand, are working with very valuable mobile data, and they're actually associated with Statistics New Zealand. But before they share that data with anyone, they strip it of all the PII, and they have a team of lawyers that basically are working really closely with them to ensure that they're using the data ethically. So it's definitely something that we have to include in our plan. And you know, when I was talking to now called the National Emergency Management Agency of New Zealand, at the time they were called something else. But when I was interviewing them, one of their concerns was the security of the data, and that they, even though they're, according to the Sendai framework, they should be just developing the national loss database. They don't have the security infrastructure in place to protect the data. So they're working with Stats New Zealand to kind of get that guidance. So yeah, it's definitely a very important consideration.
Well, thanks so much, Sarah, for your talk and for responding so well to the questions that were posed. And we're going to move on. So thank you so much. I can't imagine giving a talk at 3 or 4 a.m. So kudos to you. And I shared that on the chat, so the Q&A. So I think we all are in awe of your ability to, your resilience, I guess, to the clock. So I'm going to share again. Thanks. We'll go back to the overall agenda again, and our next speaker is James Daniel from Karlsruhe Institute of Technology, and he's going to talk about loss estimation, grade, and a tropical cyclone case study. So I'm going to pass it over to James. So thank you for joining us.
Thank you. Can you hear me all right?
You sound good to me.
Perfect. And the slides are there, hopefully. So my name's James Daniel. I'm currently at Karlsruhe Institute of Technology, as well as at the World Bank in a group called Disaster Risk and Analytic Solutions team. Yeah, I've sort of been dealing with disasters most of my life. So my dad was a flood engineer, mum was an historian, and used to get dragged around Australia to all the different flood sites in real time. And so sort of that then piqued my interest and continued on analysing disasters in real time and collecting disaster data around the world. And yeah, this is one application of sort of all of this disaster collection, I suppose, over the last years, is that we developed a thing called the Global Rapid Post-Disaster Damage Estimation Approach, which is used in sort of the post-disaster phase, also in near real time for cyclones, but post-disaster phase to try and work out or estimate the economic cost of the disaster. Now, Cyclone Idai was one of the big events of 2019, somewhere between 1,200 and 3,000 deaths, depending on how you, which estimates you're using. It affected 3 countries in Africa: Malawi, Mozambique, and Zimbabwe. And straight after the disaster, the governments grappled with the questions, I suppose, which all governments grapple with after a disaster. How do we assess the damages? You know, we haven't had a disaster of this size for a while. Where's all the data? where are the damages distributed, because obviously there's impacts across all different places in the countries, as well as, you know, what is the socioeconomic impact as well associated with this? How am I going to, you know, pay the bills after this, and so forth. Now, after disasters all around the world, I suppose a good analogy is probably the US elections. There are a lot of assessments which come out often very, very quickly, which may not have a huge amount of basis behind them. They might have historical data, or they might just be an estimate. You know, I've won the election, versus waiting to count all of the details over time, right up until the final vote, which may be, you know, 10 months in the future. And then you could give the assessment. In reality, so for disasters, we need something in between. Those first estimates are, of course, sometimes useful, but there's a sort of a sweet spot where an estimate is good enough to be able to then provide enough detail that then the governments can really use it and go ahead with their sort of economic planning. So there's lots of different post-disaster tools around the world. Obviously, GDAX comes out in real time with a lot of disaster data. These types of rapid loss estimation approaches based on a lot of historical data create an estimate for disasters. Then you have sort of another swath which are a bit slower, some coming from, you know, civil protection agencies, from commercial companies. They're often black boxes, and then they come out with an estimate. Then we start getting, you know, in the order of, you know, 6 hours, 12 hours. You sometimes get satellite studies, as well as sort of damage proxy assessments and things like this, Copernicus and so forth coming out. Then a lot of data obviously comes through humanitarian agencies, ones on the ground, and sort of hybrid reports like ReliefWeb. Then your big insurers, reinsurers will have a look at their portfolios, and they'll try to scale up an assessment based on that. You might have government institutions tweeting, using Facebook and doing these types of things to give assessments. Then you'll have research in universities, and this is where you start getting into a few more detailed assessments and a few more sort of detailed values coming out across lots of different sectors. Then you have the PDNA and DALA, and PDNA and DALA is the post-disaster needs assessments. And they're done generally between the UN, the World Bank, and the EC, European Commission. And this provides sort of the real assessment for sort of recovery needs and planning. And this often takes somewhere between 2 and 10 months. So this is why this approach was sort of wanted, to sort of fill the gap of being quick enough that we can use it for a quicker payout, which means that you can obviously help things, as well as being, you know, in good enough detail. So over the last 5 years, we've applied this to 20 major disasters globally, but we've covered every other disaster through rapid loss means. So 24/7 around the world for the last 12 years, we've been covering every disaster. But this grade approach has only been applied yet so far to about 20 disasters. We're doing Turkey at the moment as well. But yeah, it's no longer a 2 months to 10 months sort of detailed method. It uses a 2-week methodology to try and get at this assessment. So the skill is really in its analysis, and it uses all the aspects, I suppose, which Sarah had in her topic beforehand, so in her talk. So you have the hazard aspects. So you have the event scientific data, creating, you know, the footprint of the disaster, the historical damage data, and this obviously is used a lot through my CatDat database, but also through whatever databases that the countries have. Socioeconomic data, having all of those proxies and all of the building assessment sort of data, census data, everything already geocoded in advance of the disaster is extremely important. Remote sense data, social media data we use in that 2-week period. Vulnerability functions, and obviously the damage on the ground itself. So this is sort of the unique thing about this, is that it sort of mixes modeling with then all of the damage assessment which is going on in the first 2-week period to sort of update the modeling. So you might start off with your wind field, and then it will be modified by all the local aspects that you're getting off the ground. And so in the places where you know the damage, then you'll be using that. But in other places, then you'll use proxies based on relationships of vulnerability and so forth. So we do this globally for weather-related disasters, mostly cyclones, riverine floods, and flash floods. Temporal scale is really post-disaster in that 2-week period. What are the magnitude of the events for grade? For grade, it's generally the larger events. And in terms of the complex overlap events, yes, it's sort of flexible, I suppose, in terms of using modeled versus using the survey data and using the unknowns, because again, cyclones are complex. They have a wind aspect, they have rain intrusion to make the damage, they have flooding, often storm surge associated with it, and you can't usually apply a basic function to get at what the economic loss of a building is, because it's affected by four different things. And so often it's quite a difficult thing. We do use remote sense data as well, so we don't not use it, but it's often used just as sort of a checking mechanism, as with a lot of things. So we do use Copernicus, we use area proxy damage maps in the first couple of days, just to sort of check our modeling as well. But often by, within this 2 weeks, you're at least getting ground-based reports from the governments and from subnational government agencies. But it's still a very useful tool, and obviously as it improves, then hopefully we'll be able to use it even more and more as we go on. So just sort of focusing on Cyclone Idai now and sort of going through sort of how we sort of did it. So it was, as I said, quite a big sort of cyclone. By the time it hit landfall for the second time, there was about 200 km/h winds, about 10 minutes sustained. So, it was a big hit. There was storm surge. There was a lot of damage near Beira on the coast of Mozambique here. And it went inland as well. So you were still getting damaging wind speeds in Zimbabwe as well. Now, before it went in for the second time, it caused quite a lot of flooding damage as a tropical depression and low pressure system through Malawi and Mozambique. And actually you had some locations that actually got hit twice by sort of the rainfall. So you have two events where you're trying to, correlate the damage as well from the first event to the second event and so forth. So what's the first thing that we do? So what we do is that we first work out, what are the languages in these countries. So that's the first thing. As soon as you see that there's a disaster occurring, find the local languages. So for Zimbabwe, that's Shona and English. For Mozambique, it's Portuguese. And for Malawi, mostly English with a combination of other languages. And always the best data is coming out in the local language. It will then be translated. It will then be, adapted and put into other forms. But yeah, if there's one thing I can say from the last, 20 years of covering, disasters in real time around the world, is that best data and the best information is always coming from local language first. The disaster assessment process that we use is the same as any other disaster assessment process. We have sort of the pre-disaster context baseline, and that baseline is extremely important. We have this for lots of countries all around the world, obviously within the bank. So this is built from open data portals, from census data, from all different types of baselines. Of course, there'll be information, and there'll be new information always coming out from these open data portals. So during this 2-week period as well, we're always updating the baseline as well. So getting the best data for where the schools are located, what is the value of the schools, and so forth. In terms of disaster effects, we've mainly focused on the capital damages. We've found that obviously you can always do a loss assessment for the losses side of it, but in reality, that really goes beyond the 2-week period, and it is affected by so many other proxies. So we really focus on the capital damages. And we're really trying to get through to, what is the disaster impact in terms of replacement cost, but then what are also the recovery needs. So in terms of building back better, in terms of disaster risk reduction, and sort of the value of the damage and cost and so forth. And then to help, this sort of will inform then the recovery strategy. So in terms of Idai, what were sort of the modeling challenges? In the first day, you sort of get out all the information. You've got the 3 countries sitting there, And you go, well, okay, there's no pre-existing model. We've got stochastic risk models that we've built for various, companies around the world. And yes, they do cover Mozambique, but they don't cover exactly this event. And they don't cover the amount of rainfall that we were seeing, and also the combination approaches of this storm surge, of this rain intrusion, and other things as well. So we started from sort of blank for this case, because also we had the 2 landfalls and this mixed bag of damages that we were seeing. We also had a lot of delayed and conflicting damage reports, and this often happens as well, and I suppose Sarah touched upon this as well in her conceptual knowledge base, is that there are huge amounts of different conflicting reports, and that's part of this work in the 2-week period, is to sort of take the really good parts of what we can trust in terms of social media, in terms of citizens and science reports, as well as from the government, but also to throw out certain things. We can test based on the baseline. We can test, is this assessment of the government of 1,000 schools destroyed realistic? Because actually they only have 400 schools in this province. And so you can sort of start assessing all of the information which is coming out. We use exactly the same process as a normal risk model would. So we use hazard, exposure, and vulnerability. For the hazard, we start off in the first couple of days with flood footprints, with wind fields, but from all different types of wind models. Storm surge, of course, from all different types. But then as we go on through the disaster, these become less and less important, because we are adapting it based on the data which is coming in from the ground in terms of the observed damages. And of course, we need a huge amount of building and capital stock data, as well as historic and engineering damage data as well, to be able to do this. So what are the 2 key things? Well, we benchmark against historical disasters. And again, this is where the team that we have is quite unique, in that we've all been collecting our own damage databases through time around the world. And so it's it's quite nice, because we do have these huge damage databases that we can find disasters in the past, which we can then look at and then see, okay, does this make sense with this disaster? As well as the validating against damage observations. And I think this is the other key aspect of GRADE, is that it really is using the damage estimation from the ground to update a model. And this is, I suppose, the unique part of this. So in the end, what do we deliver? We deliver then the estimates of the capital damages by sector. And it differs depending on the grade and depending on the quality of information and the trust that we have in the model. So if we don't trust the agricultural part of the model, we don't deliver it. We then wait for the PDNA 2 months on or 4 months on to do the on-the-ground full assessment. But if we're comfortable with that, we've got good agricultural census data, that the land use patterns are making sense, that the yield profile in terms of the damage, say, to vanilla beans or whatever, that was actually from the Madagascar ones, but for whatever agricultural crop sources that are there, if we're comfortable with the damage functions and the damage we're seeing, then we'll give that assessment. So the cyclone impacted 3 countries, Mozambique. So this was the Mozambique assessment. And again, we split it down by provinces as well. It depends again on the disaster. So of course, when we're modeling it, we model it on a much higher resolution than this. But we find that it's important to obviously find the right resolution for the government to understand, where do I need to put my resources? And so often we scale then this high resolution back to a lower resolution where they can actually take it all in. Then we also often use economic metrics to explain it to them. Although it's capital damages, of course, capital formation takes up a part of the gross domestic product, and so gross domestic product is often a good way of explaining it to a government, especially since most governments around the world are only interested in a 3-year shelf life or a 4-year shelf life. So often they're really only worried about GDP rather than capital itself. Cyclone impacts in Zimbabwe. So obviously this comes inland, and again, it's quite interesting because the information flows are often not there within some of these countries. And so often this is the first sort of real assessment that they get before, you know, a few weeks to a month on where some of the disaster data starts coming in as well. So it differs all around the world. And Malawi as well, this was more flooding aspects, and so these were the results. So how does this inform things? Well, it goes into the World Bank regional response, so that rapid damage assessment is done. Then it will be used in terms of the response mechanisms. So in Mozambique, in Malawi, it was used directly. And then it supports also the PDNA. So the post-disaster needs assessment is often still done after this. And in all of those cases, the economic assessment has been within 10% of that final PDNA. So it's working really well, which is good. It sort of is the joining of rapid loss modeling to sort of this damage estimation. And it really only is because open data and data around the world is improving so much. Otherwise, this wouldn't be possible. And so in the end, what we can get is tables like this, where this is the recovery needs, and we know that there's about 2.4 billion, and then we go to the donors, and everybody discusses where is this money going to come from, to what percentage of it is going to be funded globally versus from the governments themselves, and then they can use this for organisation. So yeah, there's further reading associated with this if you're interested, and yeah, obviously there's a lot of aspects in GRADE. And we're always sort of refining it as well. It's very dynamic, but yeah, hopefully that gives you a little bit of an insight into what we do.
That's great, James. Thanks so much for giving us that very thorough overview. I think there's a lot of information to follow up. It's interesting how this type of information, in some cases we tailor it to specific policy needs or decision makers. In other cases, we're talking about broader public behavior and trying to influence that. And it's really the whole mix, and it comes together in what you presented, I think. We had one question from one of our presenters, from Jeff Lazo, that I'd like to raise. He says, how does GRADE compare or relate to MDAT data? So I guess the sources of data that go into your product here.
Yeah, so I mean, GRADE is a sort of a damage estimation as such. So you could think of this as one line in MDAT. MDAT would take this GRADE value and put it in their economic effects data, data point as such. So I suppose it's a little bit different in that respect. There are a lot of damage sort of damage databases around the world as well. So loss databases. So there's MDAT, there's CatDat, the one that sort of I've been collecting. There's Desinventar, there's the Swiss Re Sigma, Munich Re NatCat service, and all of these obviously have their strong points and their weak points. MDAT was based on OFDA, a 1972 database. There's some of those past disasters maybe should be reassessed and things like this. That's sort of MDAT. So again, it's always best to go back to those original sources again. So as I said, always trust local and go back to original sources. And I think we're getting to a point where around the world there's sort of each country is taking their own sort of assessment, which is good because it means that we're getting now 244 country databases hopefully at the end, and it sounds like we'll have a good integrated one for New Zealand finally as well. So yeah, that will be obviously extremely useful, because through those historical events we can often use this as one of the first proxies by using normalization techniques and things like this as to what the economic value of that event that is now occurring that it could be. And so that past event data is extremely important. So yeah.
So I should qualify the question from Jeff. He had asked that very early in your talk, and I think found an answer, but that was a much better answer, I think, that you just gave. One follow-up question. I'm not going to follow up. Jeff has a second question, but you can ask it later. Brian Golding's chimed in with a question. and I'll just read it out for everyone. In terms of warnings, we would like to be able to make these estimates before the cyclone hits. So, I mean, there's a value, obviously, in post-event evaluation, but ideally, say something before and how big it might be or how important it might be. Since you start your analysis with model data and finish with real data or data that you observe, can you say something about how well we could have predicted the damage ahead of the disaster? And maybe that relates to the validation of the model down the road. I don't know.
Yeah, so yes, this is indeed possible, and it works best for the sort of the high wind impact, low rainfall impact events. What we find is because of this mixed damage that you get through hurricanes and cyclones, the problem is that you have often landslides, storm surge, flooding, rain intrusion, as well as that wind aspect causing the damage on your infrastructure and on your buildings. And so in advance of it hitting the coast, you can obviously make these assessments based on your wind field and based on normal damage functions and so forth. But it's these four other problems that you can't really handle. And so what we find is that, what I've found at least using our models, is that it's nigh on it. It's not impossible, of course, to give that assessment, but the range of it is, 6-7 times. So you might be saying that it's somewhere between 300 million and 2 billion. And as then it hits, then you see, what is happening with, attenuation of the wind field, what is happening in terms of the flooding and so forth. You might then, with your rapid loss model, get it down to 500 million to 2 billion again. And then only with that damage estimation approach, where you really take the damage survey data and so forth, that's where it starts, getting down to 1.2 billion to 1.4 billion. So yeah, it's unfortunately, we're not at this point, I suppose, yet. But again, maybe with enough historical data or so forth, we might be able to bring it down enough to be able to use it. But otherwise, it's still possible, of course. But obviously, the ranges are just very big.
That's great, James. Thanks for that answer. And thank you very much for the presentation. It was really good. We'll proceed now to our final talk given by Jeff Lazo. Some of you may be familiar with Jeff's work in the area of weather-related economics, and he'll be talking today about a study they recently completed, impact-based decision support and the socioeconomic impacts of winter storms.
Thanks, Brian. See if I can get this figured out like everyone else to get started here.
I've got unshare. There we go.
Okay. Now I've got to get to Teams and share there. Okay, so let me bad network quality. Oh, great. So are you seeing my screen now, Brian?
It looks good to me. Just put it in presentation mode and you're ready to go.
Okay. Okay. Thank you, Brian. Thank you, everyone. It's been really fun listening to everyone else talking. I think so many good points have already been made. I'm not sure how much more I have to add. One thing I think James pointed out, made a comparison between the U.S. election and disasters, and I think that's a fairly kind assessment of the election process here, which has been a little bit overwhelming, still dealing with that. Also have to say, I was feeling sorry for myself for having to get up so early until Sarah said what time it was there. So I'm going to talk about a project which is pretty much wrapped up at this point. I did with my co-authors, and I'll show the articles here in a few minutes. A couple caveats, though. I want to say I'm not trying to represent the National Weather Service or make any representations about their policies and practices. So hopefully anything I say about that is interpreted correctly. I'm not an expert on how they're doing their impact-based warnings. So hopefully I represent that correctly, and maybe some of the people online can jump in if I make a misrepresentation. The work I'm going to talk about was funded by NOAA, largely directly by Louis Uccellini, the National Weather Service Director. And it's kind of a demonstration project or initial attempt to start to evaluate the social economic benefits of impact-based decision support systems. So if I can advance here, real quickly, I'm going to say less about the actual case study than I should, partly because the people who did most of the heavy lifting, Heather Hosterman at Apt Associates, did the technical work, so I'll try to represent that appropriately. Let's start with kind of 5 quick thoughts about this. Talk about the weather information value chain. Brian and I have been talking about that for several years, actually, and I think it plays a role in all of this. I'm going to show the references that this is based on in case you're interested and want to get into the technical aspects of this analysis, and then talk about the case study. So real quickly, and this is where I want to not represent the Weather Service, but we were looking at what's called impact-based decision support services that are being supplied now by the Weather Service, which are somewhat different than impact-based warnings. This is really decision support services from the Weather Service to their core partners, as opposed to putting out warnings about the impacts. If I'm not representing that correctly, someone let me know. So it's really about assessing the socioeconomic benefits of an improved communication process from the Weather Service to their partners, which is related to the anticipated level of impacts. And obviously every country does things a little bit differently. So I think this is kind of the approach that the US is taking right now. Want to, maybe since I'm an economist, emphasize this is trying to get an endpoint of economic assessment of the benefits of IDSS. I kind of represent that as kind of the ultimate end user verification. I think there's another workshop here in a week or two with Beth Ebert and Barb Brown talking about end user verification. I think this could really, and we've talked about this over the years as well, be a ultimate end user verification point there. And I'd also say that if there are not socioeconomic benefits, the one you need to ask is this worth doing? So trying to measure the socioeconomic benefits as an endpoint is a valid way of trying to do verification of the benefits or improvements from impact-based warnings. Also, the work that I'm talking about is a case study approach. It's kind of it's better than anecdotes, but it's not something that's universal and can be generalized to the entire country, and I'll emphasize that later. I'm not going to emphasize the quantitative analysis here. You can read the papers. If you can't get the papers, feel free to email me, and I'll try to get those to you. I'm not sure if the actual report is available online, but I can probably supply that as well. Then the other thing I'm going to talk about is the value chain before I get into talking about the case studies. This comes up across the HIWeather project. I think it's an important heuristic or tool for integrating across these different aspects. It's different fundamentally from what I'm now understanding is called value chain analysis, especially in agriculture production. It's more about the process of communication. And I'll keep pushing that idea and maybe participate in the workshop in a couple weeks on the value chain stuff. So before I get into the case study, this is kind of the value chain I've talked about for quite a while. It's not necessarily the best one, hasn't advanced as much as it should, but the basic point here is that there's many different actors, many different stages in the communication process, where from the hydromet service, the NMHS at the far left, to the endpoint on the far right, we really need to understand that process of information creation, communication, dissemination to get to the endpoint of the public or the socioeconomic benefits. And I think some of the other talks have shown the incredible complexity of the social systems, of the data needs, of the modeling approaches to try to get at what's happening once this forecast or once the information starts to go out the door. And I'd always say that weather forecasters think that weather forecasting is hard. Well, the social science side is much more messy and much more complex, I'd say. And our data sources are also much more varied, as I think the other speakers have talked about. From an economic point of view, I think it'd be useful to look at each of the actors in the process. Standard economic method would be to look at their objective, their resources and constraints, and that may be a way of framing the discussion about information quality and process and flow and how that changes between the creation at the Weather Service to the end users. Also want to point out the economic values are, as some of the other speakers have talked about, extremely complex, nonlinear, dynamic, and so it's ultimately the endpoint. The value of information is the ability of the end users to make use of that information. And I think we have to be able to tell the story from end to end to understand how that value or how that information's valued. So the studies I'm going to talk about briefly here, there's 2 papers published on this. Heather Hosterman, Jen Sprague, Jeffrey Atkins are my co-authors on these. Jen with the Weather Service, Jeff is a economist, also contracted with the Weather Service, Heather with App Consulting. We have the 2 articles, one in BAMS, one in Journal of Emergency Management. And the real reason, part of the reason we wanted to get this into GEM is to start dialogue with the emergency managers, have them become more aware of the IDSS and get their feedback and interaction on this. Also suggest taking a look at Louis Cellini and John Tenehove have an article in BAMS more focused on the IDSS kind of within the Weather Service aspects. And Brian also showed this other, the WMO economic book that we put together. That's where the value chain model that Brian showed came out of this. Also a good resource globally for looking at the relationship between Weather Service, National Hydromet Services, and economic analysis. So the case study, again, this was supported by NOAA. I was a consultant to APT on this, worked with Heather on this. It's a case study comparison, kind of a first foray into trying to actually put some quantitative estimates on the benefit of IDSS. And I'll say a little bit about how difficult that is in a few minutes. But basically, we tried to identify the IDSS pathways. We did this specifically with respect to winter storms in New York City area. It's still very high impact, but this is a case study of compared basically 2 storms that I'll talk about. We chose 4, but really focused on the comparison between 2. Some more information in the papers on those. Then we selected sectors to try to characterize the impacts either qualitatively or quantitatively, and they were chosen not as much because of the magnitude of impacts, partly, but the availability of actually information on those impacts. And then we tried to describe the value chain and illustrate the benefits, or qualitatively measure the benefits and then quantify them where we can. So first step was trying to see where does IDSS, impact-based decision support services, fit in the model. This in a different interpretation or different representation of the value chain. In this case, we realized that IDSS kind of fits in as an extra step between the forecast and warnings and dissemination. And it really is trying to strengthen the connection between the production and output of that information to the core users or core partners. And those core partners, quite often it's emergency managers, aviation managers, local and state and federal government agencies, specific, not necessarily end users of the information, but people who can benefit from the assistance of the Weather Service in interpreting and using that information. And a lot of what we found through interviews and stuff was that this is really, and this kind of relates back to I think Sarah's comments about trust and building those relationships and trust in the information. Then we assess the damages, though, are kind of, or the benefits are basically reduced asset damage, reduced service interruptions across these sectors. We didn't really quantify the human health impacts as much, but also recognizing the emergency management lays across this. Again, this is a fairly simplified representation. I think Sarah's diagram of all the bits and pieces of her, I think, her knowledge system really drills down a lot deeper into some of this. So the other thing is conceptualizing what we're modeling here. And if you think about this Northeast snowfall impact scale from small storms up to extreme storms, what we're trying to say is if you have without IDSS, the upper line there shows the impacts of that storm increasing with the size of the storm. At some point, they're high no matter what you do. But the idea is that with IDSS, we can hopefully lower the impacts of each of those storms based on different categories. And this identifies the 2 storms we're comparing in the case study, the December 2010 storm and the January 2016 storm. And the papers discuss quite a bit more about what the limitations of this are. Obviously, every storm is different times, different outcomes. So again, this is a case study. It is leading on to further work, but I won't be able to say much about that right now either. So the methods, kind of a modified sector expert elicitation. We had a number of interviews with experts in transportation, energy, ground transportation, aviation, disaster risk management in the cities and the areas around New York City. Tried to find out their protocols, the economic impacts, the extent to which these impacts could be mitigated with IDSS. Then we tried to characterize and monetize the impacts in these 3 different areas. Some of this was basically expert opinion. Some of it we dug out the data from, say, aviation transportation information. Focused on 3 areas here. One was the cost of flight cancellations, both to airlines and to customers between these 2 events. Differences in the ground transportation recovery system, that's the railways and buses in the New York City area, which is the whole area, all 5 boroughs. And then impacts on public power outages with the 2 major energy suppliers in the region. It's kind of the summary table of what we found. So this is for the 3 sectors: aviation, ground transport, and energy. The impact category is what we were trying to measure or characterize. The 2 storms of December 2010, December 16, we tried to quantify that to the extent we could, and then looked at the improvements or changes in outcomes with and without IDSS, also recognizing there was a lot of other stuff that went on in terms of emergency management preparation between 2010, 2016. I mean, after the 2010 storm, there was a lot of work in even just in preparation in, say, New York City for dealing with winter storms. So this is not all fully attributable to IDSS, but we figure a significant or a reasonable portion could be attributed there. So for instance, in terms of aviation, they went from a reactive flight cancellations to proactive flight cancellations. We focus just on New York City, but that has major implications across the whole airspace of the U.S. Basically found a reduction in costs, basically cost to the airlines and inconvenience to customers, let's say $17 million between these 2 events. Ground transportation, we were able to qualitatively assess that with discussions with the transportation systems, the MTA, I think it's the MTA in New York City, basically said they went from a recovery time of 7 days to 2 days. So from having hundreds and thousands of buses and taxis and cars stuck on the roadways to banning them before the storm, they were much more quickly able to get back to a normal system, basically by 5 days, which in New York City you can imagine is a significant improvement. With the energy, my cat is saying hi as well, so just ignore the cat. Energy, the 2 major energy suppliers in the New York City area were able to proactively position themselves, be ready for the outages, reduce interruption costs by something like $92 million. Again, the details on how we quantified this are more in the papers in the report. Again, with the references, if you're interested in those, if you can't find them, let me know. I can send them. I'm not sure and this hopefully is not breaking a law of copyright. I think I can send them, but that's a whole nother thing. So with that, I'll keep this fairly short and say thank you. And if you have any questions, be happy to hear them. And with that, I think I stopped sharing desktop, Brian, or?
Yeah, you can stop. I think Martin can pick up from there. Getting a little feedback. Okay, thanks a lot, Jeff, for that. You covered a lot of ground there, and I think it's quite clear that it's hard to separate the activities or interests of any single task team from all the rest, because there's aspects of evaluation, of communication, obviously the input forecasting information or decision support aspects from the Weather Service. We have a couple questions here, and one speaks to something that we've discussed in the past, I think, and that's from Carolina Cerudo from Argentina, and she basically makes the comment that it's important to talk about how we communicate the results of these types of studies or research to government or specific stakeholders. So how do we, I guess, take the results and make an influence, or how does that influence the way we talk about them might influence how they actually can use them?
So one thought there is, so my study, I think all three other people can have their perspective, is that's part of the reason we wanted to get our study into the Journal of Emergency Management, was to create a dialogue with emergency managers about IDSS if they're not aware with it, how it works, what it is, what the benefits are, so that dialogue can happen. Also, from an economic point of view, I think it's worth having that data, that information for the bureaucrats or the administration or the officials to say, yeah, there is an economic benefit to doing this. That's one endpoint. Socioeconomics or economics tries to quantify the social and economic differences, but that also, it does eventually translate to well-being. So I think if we can show how that well-being is improved, that gives a good way to discuss this with the decision makers and policy makers.
That's great. We had a second question as well from Yimer Uring, I think, sorry if I mispronounced your name. And that's really you basically, what perspectives other than economics perspectives would you consider to being good candidates to push alongside the economics one that you used and talked about? So I guess what other types of disciplines, I guess, and our applications?
Okay, so hi Helmer, long time no see. So I think one of the things I had to kind of skip over, I think that the value chain concept or approach is applicable to any social science. I think communication is obviously a huge part of this, that anyone could take the value chain and say, how does communication work between the different actors, different agents? How does the content of the information change from step to step? I think any social science can overlay on this as an information process, and any social science can come at this and assess it, whether it's geography, anthropology, sociology, communication. They all can add something to understanding the information creation, communication, and the decision making. I mean, decision sciences plays a role in this. I mean, Isabel's work obviously could be integrated or is a different cut on this, or this is a different cut on Isabel's work in terms of decision making. So I think any of the other social sciences could use this approach and measure this or quantify this in as different ways. So probably a lot more to say on that, but I'll leave it at that for now.
That's great. No, thanks for that. I think we're going to close the speaking session. Obviously, Jeff's the last speaker, but then we'll have a little time now for some general questions. And I gathered a couple that we didn't get to after my introduction that I think relate to all of us, or perhaps all of the speakers could comment on. And I guess in general, it was a question is, how do you, how would operational forecasters, so a very specific type of practitioner, begin making the shift to impact-based forecasting? So how can they, what should they do, and how can they do that? And I guess related to that was a second question. I'll just throw them together because they're kind of related. How do we, I guess, as researchers or people who are kind of halfway between researcher and practitioner, how do we support national service development of impact-based forecast services or warning services? So throw it out to the team to respond. I'm just gonna.
So I'll jump in first here, since I'm often happy to say things I know little about. I think that one of the approaches in the U.S. is not ready to jump right into forecasting and talking about the impacts, but taking a smaller step from the Weather Service to their core partners, they call them, and improving that connection. Are they communicating with the emergency managers appropriately? One of the things they've started to do is operationally put weather forecasters in the Emergency Management Operations Center so that they can improve that link from the Weather Service information to the emergency management. And it's not just emergency managers, the whole operations center, to interpret and understand information. And it's a two-way flow that the EMs can then ask the embedded forecasters for specific information or how to interpret that information. So it's a two-way flow that they can improve that communication. That's true whether it's emergency managers, the energy companies, the aviation administration people. So that's a first step, is just improving that communication operationally. I think that's what the focus, if I represent that correctly, in the US is with IDSS.
Any others want to talk about their perspectives on that?
I'll share from the New Zealand perspective, even though I'm very much an outsider as a Canadian here, but from what I can see, along the lines of what Jeff was saying, opening up communication between the different stakeholders and agencies. So in New Zealand, like I said, there's a lot of the informal partnerships that's already happening, but also taking baby steps. So the New Zealand Met Service, kind of similar to, New Zealand and Canada are quite similar in that we're very risk-averse countries. So the New Zealand Met Service is kind of hesitant to fully jump into the impact-based warning space. So they're working with my main supervisor, Dr. Sally Potter, who many of you probably know, to really explore the effectiveness of impact-based warning to see if all of this effort is actually worth it. So I think working in partnership with researchers is really critical. Researchers and meteorologists is critical. I lost my train of thought.
Oh, that's good. That's good. I'm just going to, before I go to Isabel and James for some feedback, I just raise a point made by Bob Goldhammer, just saying that sometimes you have to grease the wheels before you can push the information out. So he suggests that it's been nice to find a much better way to get the information into the newspapers, or I guess conventional media or social media, so that they have a better understanding of what's coming and how the actions could proceed if you take advantage of this information that's being provided. And that a little preparedness goes a long way, I guess, is the essence of his point. Isabel, James, do you want to follow up? Any comment?
Yeah, so from my perspective, there's obviously so many different players involved. So you've got your governments, you've got your insurance agencies, you've got citizen scientists, and then you've got other companies as well. And then you've got the media on top of that. So there's 5 sort of key groups in the post-disaster setting, or even in the pre-disaster setting. And the problem is that they all have different sort of ways that they want to get out the information. They also have very different ways that they approach the problem, and they also have completely different definitions as well. And so within that government, you've got then different structures depending on which country you are in the world. So in some countries, you've got 4 levels of disaster risk management agencies. So you go down from national to provincial to municipal and then to one below. And all of them sometimes have functioning disaster managers at each level of that. And then you have some countries where you've only got a national level agency. Then sometimes you've got competing agencies within that government. And then from those other 4 groups that I also talked about, there's always these competing interests even within those groups. Then you're trying to mix it all together. So I haven't seen a country yet which has successfully brought all of these 5 groups together yet. And I know there's a lot of research going out into the insurance industry versus governments, firstly, as just a starting point, as well as insurance industry to researchers. But other than that, it's unfortunately, it's a very, very complex problem. And without, participatory modeling, stakeholder engagement workshops and things like this, it's a difficult place to start. So that's just sort of my perspective, and it doesn't obviously give any solutions whatsoever, but it's just sort of putting it out there.
Last comment to you, Isabel.
Okay. For the impact-based forecast in France, at least, Météo France is really going into the direction of integrating the vulnerability in the forecast now, and but they start to closely work with civil security services to somehow see how to better. Of course, their responsibility is quite mixed because they have to warn directly the people, but in the same time you have the civil security related to the prefectures, administrative areas, who also do an alert. this is very much tied together, and so you need to figure out what is the limit for one and the beginning of the work of the other. But so that's why it's very, very important that they decide together and they see how they can really integrate those information, because the detailed information is coming from civil security, but in the same time also meteorological forecast also talk directly to the people who need to take decisions. I mean, everyone in front of a crisis needs to take decisions. So it's very difficult to target this problem, and there's responsibility related to this. So, but I think they take this direction at least to find a common solution, and yeah, to figure out how to do that. So, and I think many meteorological services are going this direction and try to find the good path for that.
That's great, Isabel. I think there's a lot of work to be done, and building these partnerships is certainly a big part of that. Sustaining them is another challenge, but we'll deal with that on another day. I want to thank everyone for participating in the audience from all around the world, and especially those who had to get up really early or stay up really late. I apologize if we didn't get to your question. Put them in the chat room. We'll follow up if we can. We can give you the contact information. It was on the first slide. This will be recorded and you'll be able to review it at your leisure. And just to highlight now, I think you should be seeing my screen, and that's the next seminar is November 11th, and you can see the times there, but that will be followed by 2 more. And that will lead us into the bigger workshop, December 1st to 3rd, where we tackle those 3 primary high weather initiatives. If you're interested in joining the Impact, Vulnerability and Risk task team, please give me an email. We can chat. It's voluntary, obviously, so we take advantage of everyone's time. And as I said, there's lots of work to be done, and no lack of trying to work to transfer it and make it useful, the research that we do. So with that, I really want to thank Martin again at WMO for really helping us coordinate this session. He has a lot of patience, and I appreciate that, and I'm sure the next set of hosts will have the same feeling. And especially thank our speakers. So Isabel, Sarah, James, and Jeff, thank you so much for participating, and hopefully everyone can participate again in the workshop in early December.